Uh, yeah, thanks. Um, Chad and I have known each other, well, since we both started at JC 21 years ago. So I'm this is going to be fairly general. There might be questions, and so I'm going to keep it kind of short, I hope, and then we can have some questions because I'll bet there are going to be some questions that arise from this. Next chart.
You've got control. You've got control.
Okay, there. All right. Sorry, there was a lag. This is a little bit about my bio. I've been at NASA for 21 years or so, and I've been kind of in this arena. In 2014, I got to be the tech lead for navigation for human spaceflight, and then I've been in this position that I'm in right now for 3 years. And it's been kind of a learning experience because it's not necessarily, I'm not focused necessarily just on spacecraft, but aircraft and UAVs and all kinds of things like that. So I've had a and landers on the moon and things like that. So it's been kind of a learning experience for me, and it's been fun. So here is what I'm planning to show. We're going to talk about first. We're going to talk about autonomous navigation, actually GNC, but focus on navigation uh, for human-rated missions, and then as well, I'm going to talk about for landing missions as well. So some of which are human-rated. So first, talk about Artemis One. Artemis One happened about 3.5 years ago. Yeah, at the end of 2022. Um, it was uncrewed, and it was a 26-day mission, and it was the first time we actually flown this vehicle. And we went into what was called a distant retrograde orbit, which was a orbit in the Earth-Moon system. It was actually orbiting the Earth, but on the other side of the Moon, and it was there for the better part of the week. It happened over Thanksgiving. I mean, that phase of the mission happened over Thanksgiving, so I spent uh, Thanksgiving in mission control. So that was a rather memorable one. And then it was like I said, a 26-day mission, and it was the first time we had actually flown a human-rated mission out to the moon in 50 years or so. Um, so that was pretty exciting. We learned a lot. There were a lot of scary moments with regard to sensors and things like that, and we can talk about that if y'all want to do that. And so it set the stage for Artemis II. Um, but one of the things that happened is that we were testing a couple of things: the heat shield coming in at lunar velocities, but also a skip entry. So basically, to extend the range, they had a skip entry where you enter the atmosphere, you skipped out, and then you came back, and that exposed some flaws with regard to the heat shield, which we're still contending with, having to do with material, a material called Avcoat, which was actually done during Apollo, but it was allegedly made better. And so making it better, it exposed some flaws in the understanding of the material properties and this, that, and the other. And we can talk about that if you'd like to. So yeah, so that was in 2022. And so as most people are aware, we just flew Artemis II, and that was a 10-day mission. It launched on April 1st and landed last Friday. And it was the first crewed mission of this particular spacecraft. And one of the things they were testing was the environmental and life support system, as well as the wastewater, i.e., the toilets. And as you are probably aware, there were not a few issues with the toilet. I'm not a person. I was going to say a toilet guy, but that wouldn't be appropriate. But I don't have much, actually, anything to do with it, other than one aspect of it, in the sense that unlike Apollo, Um, they, if you've seen Apollo 13, maybe you haven't, maybe you haven't. One of the issues had to do with the carbon dioxide in the cabin, and so what they decided on the Artemis missions is to vent the carbon dioxide and the humidity off board, and vent the wastewater as well off board. And that there was a problem with the vent on the wastewater, we think, and it had to do with the clog associated with the vent and the filters. And I'm not tied into that other than peripherally and how it kind of affects the GNC system. But the ECLS, the environmental control and life support system vent, which is the carbon dioxide and the humidity, it is continuous. So it acts like a little ion thruster all the time. And so you can imagine what that does to the trajectory, which was a major headache. And this is something I'd been worried about for the last 10 years. And it turned out to be better than we imagined in terms of the propulsive or the impulse that came of it. But it was actually far lower than we imagined, and that was not a good thing either in terms of our modeling. So we had in the middle of the flight, I can tell you a story about that. We had to uplink a new set of parameters. We were modeling these kinds of vents in our filter as a Gauss Markov process, a first order Gauss Markov. I think you guys do that too. From what I gathered in the last presentation, you do similar things than we do, which was kind of fun to hear, by the way, talking about some of the same issues in terms of sensor modeling and small angle approximations and things like that. So we have to contend with the same sort of things. So this was Artemis II. From a GNC perspective, it was positively boring. I mean, in looking at the data, there were no surprises other than that there were no surprises. And the people on the Polaris console, which is the GNC console, were so bored that they were trying to find things to do during the flight, including trying to figure out which astronaut was exercising at any given time based upon what they were seeing on the navigation, on the accelerometers and the gyros. And I can tell you a story or two about that too. So this was Artemis II. One of the interesting that happened is that they did what was called the Proxops demo, and you can kind of see it if you can see my cursor down in the far lower right, I should say. After on the first about 3-ish hours, 3-ish hours after launch, when they were on this initial orbit, this initial highly elliptic orbit, they did what's called a Proxops demo. You can see it kind of in this picture, which is kind of here. So it occurred in this part of the flight, immediately after the first periaps passage, in which they separated from the upper stage, the ICPS. So the ICPS did this large burn where it was an apoapsis raised burn where they raised the apoapsis to a 24-hour orbit. And so on the outbound leg, they separated from the upper stage, and they did a Proxops demo here where they turned around and they flew close to it, and they were trying to figure out what the handling qualities of the vehicle were, because this is the first time any human had actually taken over control. And it was Victor Glover who did that test, and it was kind of fun to watch, to listen to him as he was doing it. It was so smooth, and so they did a Proxops demo, and they did a couple of other piloting demos, but this was the most significant of them all. And then they did the translunar injection, and then they were on their way. It was a free return trajectory, so they didn't have to do anything. And it turns out that the navigation system that we worked on was flawless. In fact, they didn't have to do the first 2 trajectory correction maneuvers because they were so small, and the translunar injection was so accurate. And one of the fun things about that is that the translunar injection was actually using an algorithm that I helped with way back in the 2005 to 2011. We developed what was called the 2-level targeter. which was the first time a targeter was used on board a cislunar vehicle. During Apollo, they didn't have a targeter; they just had guidance laws. And so this was a cislunar targeter that, and it wasn't necessarily designed to do the TLI either, but we actually were able to harness it to do the TLI, and it was spot on. The guidance, the targeting, the control, the nav was just perfect, so that we didn't have to do anything. And then, like I said, the venting, we thought we would have to do more maneuvers because we were expecting more venting. Turns out we didn't have to do as many maneuvers because the venting was a lot lower than we imagined it to be. And so that meant that we were able to wave off the maneuvers that were on the first part of the mission. We did the third outbound trajectory correction maneuver. And then on the return leg, we did all three of them. We had three planned. And by that time, enough perturbations had built up because of the venting and because of all the jostling they had to do with regard to the wastewater system. They were doing maneuvers. They were reorienting the spacecraft in case there was ice that formed on the vent and all that kind of stuff that went on. And so we did the three correction maneuvers, and then the entry. We acquired GPS on the way back. When we were under the GPS shell, the entry, we didn't do a skip entry, it was a direct entry. And on the other side of the blackout, it acquired GPS satellites, and the nav was just spot on. It was right down the middle. And we landed within 1 nautical mile, and most of that was because of the winds under the chutes. The nav system, what we could tell, was off by about less than 10 feet when we landed. So incredibly precise. Everything went according to plan, at least from a GNC perspective. So that's kind of an overview of the mission. I talk a little bit of the navigation. So the navigation was it always had to be on. So the phrase that we had was "never don't navigate," which is, it's bad English, but it basically is what we had to do from pre-launch all the way to post-splashdown. It was on, and so nav is one of those functions that is not. It operates across all phases, so it's not phase specific in that sense. But what we had is 4 instantiations of the multiplicative extended Kalman filter. And I think you guys use Kalman filters or something there akin to it. And so it's a variant of the extended Kalman filter, which is a variant of the Kalman filter. So we've got 4 instantiations of it. We've got the atmospheric EKF, which is used during pre-launch, ascent, and entry. And it's a couple translation rotation filter. So it's got attitude states as well as translation states, i.e. position velocity. And it's got GPS states and pseudo-range biases and all of that good stuff. So once we get on orbit, we transition into what we call an Earth orbit EKF, EO EKF, and an attitude EKF. So basically now we separated it into translation and attitude, and each of these filters are different. The attitude filter uses uses the gyros coming from the IMUs as well as the GPS receiver. And the the attitude filter uses the gyros and the star tracker measurements. We've got 2 star trackers, and I'll talk about that in a moment. And then the Earth orbit EKF uses the GPS receiver and the accelerometers. And then once we get out of the GPS constellation, we transition into a cislunar EKF, and that uses planetary limb and planetary limb measurements, and that is used primarily and ground nav updates, and that is used primarily in the case, or we would certainly use planetary limb measurements in the case that we lose communication with the ground. So that permanent comm loss situation where now we have lost communication with the ground and the spacecraft's got to return the crew safely to Earth, regardless of where it is in the cislunar space. So it can look at the Earth and the Moon. And so one of the things we developed prior to Artemis 1 and certified it on Artemis 1 was this ability to navigate using Earth measurements, limb measurements of the Earth and the Moon. And so we developed that prior to Artemis 1. We flew it on Artemis 1, we certified it, and we did some further checks on Artemis 2 because we learned a lot. Because Artemis 1 was a learning flight. And from a GNC perspective, Artemis 1, it was stressful. There were a lot of issues that came up that we weren't necessarily expecting. And so we were able to fix them. And so Artemis 2 was amazingly boring. There were no surprises at all, other than the fact that we had no surprises. So the split design allows us for the ability to use different filters for different phases of flight. Now we could have and we could have done a monolithic filter, one filter to rule them all, to rule all phases. We chose not to do it just in terms of testing. We could test each one kind of in its appropriate phase, and then if you made a modification, say to the cis-lunar portion, you didn't have to retest all the atmospheric stuff. It would just affect that phase. So we could have done it in one. We chose not to. And by the way, each of these filters are not insignificant in size. So, for example, the atmospheric EKF, the ATM EKF was a 40-state filter, and we have 3 copies of it. Because we had 3 IMUs, and so each IMU each filter was associated with a particular IMU. So you had 40 states times 3, and that was operating on a not a modern flight processor. It was basically a early 2000 vintage kind of computer. And we were able to do, and Chad and I worked on that early on in terms of how we would formulate it such that it was computationally efficient as well as numerically stable. And so, that was the split design allowed us to reuse some of the guts of the EKF. Here is a little bit of a flow chart. With respect to the with the architecture, and so one of the things that was major on Artemis 1, like I mentioned, was the use of OpNav, and you can see here that you have this camera, this center part of it, and the thing about it, and I'll show it on a subsequent chart, is that we had to use camera measurements which were in a different part of the spacecraft and were separated from the IMU in our filter. And so we collaborated with Texas A&M, West Virginia University at the time. John Christian was there. So this was a collaboration in terms of developing this OpNav capability, because if you know anything about the Apollo program, they had an OpNav capability too, but it was basically the astronaut in the loop. The astronauts would look through a sextant, track a star, track a planet. We didn't want to do that on the Artemis program. So everything was autonomous, as well as automatic. So we were able to test it on Artemis 1, which didn't have crew, obviously, and we were able to certify it. So you get into a particular activity, and then once you got into the activity, which was part of the sequencing, the spacecraft would point to stars first, and calibrate the camera, and then point to the planet, either the Earth or the Moon, do its thing, get measurements, and then when that period was done, it would go back into a tail to sun attitude, because one of the major aspects of flying spacecraft, which is kind of a little known secret, is that thermal is king. So we're always worried about what our thermal attitude, what our thermal profile is, and we don't want to get too hot or too cold. And so, unlike Apollo, we didn't do a barbecue roll. We actually did a tail to sun, just to keep everything just so. So anyway, so this was we had three IMUs, we had two star trackers, and two GPS receivers. Turns out that the cameras were not on the crew module. They were on the crew module adapter. And here's a picture of where they are. So the crew module is up on a different part of the spacecraft. And so now you have two star trackers on either end. This is what's called an optical base. So you have two star trackers there, and the optical camera is mounted right in the middle. So the thing in the middle is the optical camera. The thing that's so on either side are the two star trackers. You can see the star trackers. You can see the baffles here. That's that cone-shaped thing, which was meant to be a sunshade or so that no stray light can get into the star trackers. And the camera has a similar baffle, and it's simple. It's not a very fancy camera by any chance, which was one of the things that we had to contend with. We weren't given the luxury of having a specialized optical camera. These were the same cameras that were used that you've seen the images of. If you've seen the images from Artemis I, they had these GoPro-like cameras on the tips of the solar arrays, and these were the same cameras. Now we got to say, okay, we don't want a color, we want monochrome, and we can design our we had custom made our own lens. So it was just like the others, just with different lenses and just monochrome as opposed to color. And then we mounted it on the crew module adapter on an optical base, and that was very stable. And so now you had this big lever arm between the IMU and the star trackers, and the same lever arm between the IMUs and the camera. So that was a challenge, and we didn't know whether it would be a challenge and so we assumed it would be, and so we planned for the worst case. It turns out that in Artemis I, we found that it was not, it was the misalignments were very stable. So once you calibrated one time, it stayed stable pretty much the whole flight, even though we modeled it as a Markov process, ECRV with a fast time constant, and that was annoying. But anyway, we learned, so we retuned it for Artemis II with a much longer time constant, and it worked well. We would periodically check the misalignment, and it was pretty rock solid. So those are some of the things that we observed. So what was different? I think I've talked about this a lot already. ECLS, the humidity and carbon dioxide that via and I'm not I guess chemical engineer that designs all these cat beds and things like that. But that's what it is. And so it would vent periodically for the atmosphere, depending and so the PSA vents were continuous, but then they would there were two of them, two cat beds, and so one of them would be exposed to the crew cabin, and the other one would be exposed to space, and so they would flip, and then when it was exposed to space, it was still venting, and so we had to model it kind of as an exponential with a steady state, because when it opened the first time, it would release a puff of cabin atmosphere, and that would cause a perturbation, kind of a spike, but it was decay down to steady state in about 2 seconds, and then it would stay open for 30 minutes, depending on the phase of flight. If the crew was asleep, it would the period of this would be every 30 minutes. If it was exercising, if the crew was exercising, it would cycle every 8 minutes or akin to that. And then of course there were the wastewater vents, and that was, I guess, the biggest challenge of this, that the wastewater, the toilets weren't able to be used, and that was not a fun time, I'm sure, for them. So the biggest concern was the PSA vents, which were, interestingly enough, in terms of impulse, they were 10 times larger than over that period. They were 10 times larger than a wastewater. and the strength had large uncertainties pre-flight. We were told by the manufacturer that that there was a 50% margin on the numbers they gave us. It's like, okay, what do I even do with that? There was no statistics, there was nothing, so I had to come up with ways of trying to statistically express what they meant because they didn't know what they meant. So we had to make assumptions and anyway, prior to flight, I came up with a way of based upon ground tracking data to be able to estimate what those particular events were, um, and to be able to upload those new the updated quantities associated with those particular events up to the spacecraft. So, I mean, it had a significant impact on the trajectory. We were worried that it would be really bad. It turns out it was not bad at all, which was a shocker. So that's one of those things that we did. So how did nav perform? I mentioned this already. For onboard filters, performed spectacularly. More than 1 million measurements were processed by the four filters over the period of, and only two were ejected, and they were primarily OpNav, and that was because we were kind of playing around with things, and we decided to see what would break the particular filter because once again the operators were kind of bored, uh, and so they anyway, so worked spectacular. On Artemis 1, we didn't reject a single measurement. So that was that we had tuned it so conservatively that it wasn't well, I was surprised, but I guess in hindsight it's not surprising. Now we tightened up the tuning based upon Artemis 1, and so we were trying to explore where the limits are within and this kind of thing happened on the return leg where we were safe. Even if we had lost comm with the ground, we wouldn't necessarily have to do anything. So the IMUs were amazing. They were able to pick up various crew activities. We could tell when the crew was exercising, when they were sleeping, and even during the toilet. Those few times they had toilet flushes, we were able to pick that up. In fact, they were so sensitive that we could tell after several days which astronauts were exercising. Not just that the astronauts were exercising, we could tell which ones. For example, Christina was the least aggressive in her exercising, and Victor was the most aggressive. And Reed and Jeremy were kind of in between. So we could actually tell which astronauts were exercising based upon the signature that we were seeing in the IMUs. So overall, no surprises, at least from a GNC perspective. Extremely boring. I didn't sleep much during the entire flight because I was worried, because I think I knew too much. And we already talked, the Polaris console had to find ways to entertain themselves because it was so boring for them. I'm going to switch over and talk about landing because one of the other worry beads that I have and one of my problem children right now is lunar landing and guidance, lunar landing guidance and navigation. Lately, over the last couple of years, there has been a great deal of interest and activity with respect to landing on the moon. So the Artemis program has got the human landers that haven't flown yet, and then you've got the CLPS, which is the commercial lunar provider services. These are these little things that are landing on the moon. So far, there have been 4 attempts to land on the moon. Only one of them has been successful. Intuitive Machines had 2 rather spectacular failures. At least from my perspective, I was leading the investigation board for NASA in terms of what happened, and they were all nav related, specifically algorithm and or sensor related. So CLPS is the program to facilitate commercial companies to deliver payloads to the moon, and so they were expecting, I think. Don't quote me on this one, but they were expecting about 10 failures over, 4 failures over 10 missions. Well, of the 4 missions that were launched to the moon, 3 of them were failures. So not so good. They were technology demos. They were scientific. There were scientific payloads, but the problem was they had tight funding constraints, and tight schedules too. So that's never a good thing. If you're after success, there's got to be some thoughtfulness that goes into that. And so that's rather a problem. Um, the navigation is daunting, particularly for the autonomous landers. Very unforgiving lighting, shadows, due to shadows, and there's harsh environment, temperature swings, no atmosphere, that sort of thing to ameliorate some of those effects. And we already talked about that one. Yeah, so Firefly was the only lander that was an unqualified success, and it landed almost exactly a year ago. On and So that was really, really fun to be part of. I got to be there during the landing, at least in at Firefly in Austin, and that was a blast. It landed perfectly. It landed within 30 meters. I want to say 30 meters ish of its designated landing site. The nav performed very, very well. And we can talk about that if you guys want. What am I doing here? Okay. So why is there a problem? Tight funding constraints. Using COT sensors, lower cost IMUs. They're basically MEMS IMUs like that. Terrestrial grade LRS. Most of them are derived from military kind of uh, um, vendors or vendors that supply these kinds of things to the military. Um, Unfortunately, there's a tendency, and this was the cause of a lot of this stuff. There's a tendency to treat both these sensors, the IMUs as well as the LRFs, as black boxes, and they're certainly not. To really complicate matters is that there's a reduced sense. All of them have reduced sensor testing camping. So not only are these COT sensors, but they're not tested enough, and they're certainly not tested in using a relevant trajectory. And so limited system level. There's almost no system level testing. At least there weren't. They're not tested over the entire operational envelope, and that's hard to do because a lunar landing trajectory is not able to be reproduced on Earth because the atmosphere helps on Earth, and the velocities are just unnatural to fly on the Earth. So system level is almost non-existent. And then NASA has part of the blame too. Very limited NASA oversight due to contractual constraints. In fact, you had to use the right words in order to communicate with them. Unfortunately, GNC was treated as a known commodity because the propulsion system got all the attention. So, what the challenge is navigation mostly. The optical sensors are ready for prime time. TRN, Chad in his dissertation works on crater nav, and there's been a lot of advances in the last 20 years in terms of how these things are going to be used. And yeah, this kind of stuff has worked quite well, and Firefly got it to work amazingly well. There's active TRN in which it's both cameras as well as laser rangefinders, or just laser rangefinders by themselves, kind of like the cruise missiles used to use. Laser rangefinders, they're those which are eye safe have got lower operational range, less than 5 kilometers, and the link margins are very, very tight. Then there's lidars. Scanning lidars versus flash. Is flash ready for prime time? I'm doubtful, or a combination of the two. So, and then how do all these sensors work in a vibroacoustic environment, in a harsh radiation and temperature environment? So these are some of the challenges. So how do we address the challenge? Well, one of the other things is that hazards are a particular challenge at the lunar South Pole, which seems to be where everybody wants to go, because the elevation of with respect to the sun is very low. It's like driving. Think of driving around sunset, but where the sun is right at your eye level, and that's the case all the time. And so hazard relative nav is a necessity because there are a lot of hazards, even at these landing sites. And then algorithms that can reliably process HRN and TRN types are non-negotiables. You need them because you need to be because one of the requirements going forward is not just a safe and upright and stable landing, but a precise landing. So nonlinear estimation techniques are of absolute necessity. We absolutely need to get past the old EKFs. But be sensitive to the computational constraints and to be able to guide and control and nav in the presence of hazards is a challenge. So this is not an easy problem. So we're working it. So we've had some successes and we've had some not so successes. But the bottom line is that landing at the lunar South Pole is daunting. The shadows, hazards, thermal environments, schedules, especially now. And then there's a tremendous amount of collaboration among countries. In fact, I work with my European friends a lot, and thanks to the Artemis Accord. In fact, I've gone to Jena, Germany, Jena Optronics, and I'm going to be going back there probably. And I work with those guys very closely. In fact, the Artemis source module is provided by ESA. And I think that's my last chart. I'll be happy to entertain questions.
Chris, you can't hear us on this, can you? Can you switch that, Tim? Can you hear us now, Chris?
Yes.
Okay. First of all, thank you for the presentation. We can entertain just a couple of quick questions.
Thank you so much, Chris. That's very enlightening. We learned about this. A question particular about navigation. Talked about yes. Can you hear me?
I didn't hear the question, but Chad, could you repeat it?
Yeah, he's in the middle asking it. Just
sorry.
A second.
So, and very simple. IMUs was GPS, EKF. This is standard navigation. My question is, beyond GPS constellation, you said there is start trackers and there is optical camera that are used instead of GPS. Can you give us a bit of insight? Because we feel that IMUs only will not be sufficient for navigation in absence of GPS.
So did you catch that? He wants to know.
I think so.
Past the GPS constellation.
If I heard the question right, it was IMUs are not sufficient, and you need other sensors, and that's right. That's absolutely right. You cannot navigate to the surface with IMUs only, even though some companies have tried. You need several sensors. You need cameras in order to give you information about the lateral about the cross bore sight range, if you will. You also need some sort of range measurement. I'll call it that, which is usually from some sort of laser rangefinder or radar or something like that. That would give you altitude information. And one of the challenges is that. So you need to have, in my opinion, you need to have at least some sort of visual and some sort of altitude measurement. So lidars can be really helpful, as can radars. And some of these lidars, even the scanning lidars, are really good. The problem is the rate at which they're coming in. So, for example, for the hazard detection and avoidance phase, you need them to come in around 10 hertz, and we're not quite there. We're getting there, but we're not quite there. So yeah, you can do it. You can get to a certain point on IMUs only, but then once you want to land precisely, you need to have altitude information, and you need to have cross information as well, so that you can land where you want to land and avoid hazards.
So
I don't know
Chris,
if that answers the question.
Chris, in cislunar space, I think this may be more to Mahmoud's point or question. In cislunar space, what type of measurements are you using to get to bound your positional covariance and keep it from growing?
Yeah.
Is it all Imaging from the
Okay,
ground.
sorry. Yeah, so we're using optical. So we're using looking at the limb of the moon, and then based upon the limb of the moon, we can get bearing and we can get range. And then we do the similar thing for the Earth. Now that's a passive thing, and the range information, is, especially for the Earth, is very limited. It's got a large covariance associated with it, but it's sufficient for us to be able to return the crew safely to Earth. So the other thing that we're looking at, certainly around the moon, is that the plan is to get a series of satellites like GPS, in which we would get information from the satellites that we can actually get RF. It's going to be some sort of radio information. And then the other option is to put beacons on the surface of the moon at appropriate points and have the beacons give you information. So yeah, there's the Lunar Com. It's, I forget the acronym. It's navigation, com, and something else. But it's basically GPS. It's a combination of TDRS or communication satellites and GPS around the moon. And there's some companies are allegedly going to launch that kind of thing over the next few years, or over the next few months. I'll believe it when I see it. I'm expecting it to happen over the next year or two, but not any more recent than that. So yeah, so that's in cislunar space. It's pretty much optical. When you get close to the moon, it's going to be optical and on these kinds of relay kinds of satellites. And that's pretty much it with regard to navigation in cislunar space.
Thank you.
Would anyone else want to ask a quick question here? Let me move on to collision avoidance. Oh, one more.
I'll take your chance. So you said that we need to move beyond all EKF, look into nonlinear estimation. Do you see like why you see the EKF is not sufficient? So you really have successful mission. You said it was boring because everything did work.
Yeah, what's motivating the need to move beyond the EKF with the TRN and the HRN?
Because these sensors are inherently nonlinear, and some of the information we're getting, and quite honestly, if you look at the probability density functions, certainly when you're in lunar orbit and things like that, the probability density functions are not Gaussian associated with the navigation position states. They're more croissant or banana shaped and stuff like that. And the EKF just won't work there in terms of, it'll give you a covariance, but is the covariance right? And so we're moving towards at least understanding some of these things from a navigation / orbit determination perspective, so that we're moving away from these, certainly with regard to orbit determination, we're moving away from the old batch least squares, stuff like that, into more of these nonlinear estimators, which would give you a better idea of the PDF. And if you want to derive a covariance and a mean out of that, you sure can, but that's not going to completely describe what your probability density function is.
All right. Thanks, Chris. We really
Sure.
appreciate it.